So this is going to be a brief video on Chapter 9, Section 2. What we have here are some familiar questions that maybe we've seen with limits, and we're going to approach them a different way. So feel free to pause this video and try to answer some of these questions. So here's the first question that you should be able to answer, so please pause, try to answer this question. All right, so hopefully at this point you've answered it. And so the first thought of any limit is maybe just try to substitute and hope that something good happens, and good being that we actually get a value. So if we substitute in 3 into the numerator denominator, and unfortunately we get 0 over 0. And so 0 over 0, remember, is an indeterminate form. Can't get an answer. We don't know what that really means. Lots of ways to think about that. Just a side note that if I say this, then I'm really saying this, and well, n really looks like it could be anything. So next thought. We could definitely, for this question, factor the numerator and factor the denominator. And if we do that, then this really holds the key to the question, because now I can tell that there is a common factor. There is an x minus 3. It is the reason we're getting 0 over 0. But the limit is still going to exist. This is, again, really just a hole in the graph, which means if I resubstitute over here, the answer is 4. So we've seen that before, and what I want to do is look at this, maybe look at one more of these that we've done. This one, how about the limit as, maybe this one is also x is approaching 3, of 2 to the x minus 8 over x minus 3. So looking at this question, we could do the same thing. We try to substitute in 3. We can already see it's 0 over 0, except here we cannot factor. Now, if you remember, this is a question that we've seen before when we saw the definition of the derivative, because this should, I hope, trigger a thought as to what I termed the alternate definition. So it's not involving the h, but its limit here is x is approaching a, and it's still a difference quotient, still the change in y over the change in x. Well, to answer this question then, I can almost just kind of match this up and go, okay, wait, a must be 3, because that's the role here, and I see a 3, and I see this is f of a, where this is f. So, okay, so 2 cubed is 8x. Okay, so really all of this is really just saying when f of x equals 2 to the x, what is f prime evaluated at 3? That's really what this question is asking. So what is f prime of 3? Well, the derivative of 2 to the x, we should know, is 2 to the x times the natural log of 2. And then, so if x is 3, this ends up being 8 times the natural log of 2. And so that's how we've looked at a couple of these problems before. So what I want to do is look at something called L'Hopital's rule, okay? There's an L there. There's a couple spellings of this. He was a French mathematician. You can look him up if you're interested. And so he makes this statement, and so I think I have it here on another screen. And we're going to try to prove this a little bit. So if we're trying to find some limit of some quotient, okay? And if I get 0 over 0 or infinity over infinity, then the limit that I'm interested in, which is the original problem, is the same as the limit, so approaching the same value of the derivative of the numerator divided by the derivative of the denominator. So this is not quotient rule. That's not what's happening here. We're just saying that the derivative of the numerator, derivative of the denominator here, nothing else than that, would give us the same answer. So if I flip back to these problems that I just started with, So in this first problem, if I substitute in 3, I got 0 over 0. That was the indeterminate form. So L'Hopital's rule says the limit as x approaches 3 of f of x over g of x should be the same as the limit as x approaches 3 of their derivative. So I could take the derivative of that function, so that's 2x minus 2, take the derivative of that function, which is 1. I can now re-substitute, try to find that limit, and we can see that that answer is 4, which is the same answer we got here. Same thing's going to work down here. In fact, it is a nice way to maybe solve a question, especially if you don't recognize that it was a derivative, because as long as I have that indeterminate form of 0 over 0 or infinity, I could do this. So take the derivative of the numerator, derivative of the denominator, so the limit as x approaches 3. So this is just going to become the 2 to the x times the natural log of 2 over 1. Now substitute in 3, there's our 8 natural log of 2. Now, why? Like, that seems strange that I could just go ahead and take the derivative of each of those pieces without actually, well, it's not, again, it's not quotient rule. It's not like I'm just treating just like lines and then somehow I'm getting the result. So let's see if we can justify it here a little bit. I'm going to show some, oops, wrong screen. I'm going to show some steps. And then go from there. So 1 second. Okay, so I have here just the kind of the steps I'm going to just kind of outline here for as to maybe why this is true. So if I start with this statement in black, which is really the conditions for L'Hopital's rule, we have the limit as I'm approaching x is approaching c of fx over g of x, and if I calculate f of c and g of c, they're both 0. So there's my 0 over 0 indeterminate form. So when I think about f of c and g of c, if they're really 0, then it wouldn't change anything if I just subtract 0 here and here. Now, why might I do that? Well, do you notice that if I'm wondering or thinking that there's this connection to the derivative, then shouldn't I have like a delta y and a delta x that's some limit, that alternate form again here? So that's maybe the reason to do it. Now, the next thing I could do is something like this. Now, if x is approaching c, you might argue that I'm dividing by 0 here, but what I'm effectively doing, I shouldn't be changing the limit, because if I multiply by like the reciprocal of this, and I put this here, basically again, I just have this x minus c in common, which would be like a hole in the graph, which shouldn't be changing the value of the limit. So now if I've done that, so this limit should be the same as this limit. But properties of limits lets me maybe rewrite that as couple limits. And now, looking at this, I hope you really can see the fact that this is a derivative, that this piece here is really that alternate form. So that would be like that f prime of c, and this piece here would be g prime of c. Now, it does seem like I've lost a limit here, but if I think about dividing these functions, and if they're continuous functions, which they should be if we're doing this, then, because they're differentiable, then, well, putting a limit there in front of it wouldn't actually change any answer then either, because if they're continuous, evaluating the limit as x approaches c would be the same. So that's a really quick thought, that this limit must give the same value as this limit. So let's look at a couple of quick examples here of how that might happen, or what that would look like. Now, maybe we should step back and point out that there are other indeterminate forms. And so we've seen this one before. This one I've kind of mentioned today, but in a lot of ways they're related to each other. There usually is a manipulation, algebraic manipulation that I could do messing with the fractions to turn one of these into others. So here are other ones that really, when we get an answer like that, we should be careful that we think we understand what it's saying. Sometimes people are really bothered by the last one. I think I have an example here, or you're going to see an example in your homework where that one comes up, where you might first think that's what it is, but with a manipulation, it's actually a different result. So real quick, here's an infinity times 0 example. Like if you'd look at this, you might say, well, if x is approaching 0, then I really have 0, and if x is approaching 0, that's then getting large. 0 times infinity. And you might be tempted to call that maybe 0, or maybe infinity, or maybe a value, but really, again, indeterminate, because by a manipulation, we can actually see in this scenario that this is actually the value of 1. Now here's another example that is very similar, right? Because if x is 0 but positive, then this is 0. This is going to be approaching infinity. This looks like a 0 times infinity. But with the similar manipulation, this is 1 over x to the 1/2. So if x is approaching 0, you see this is very different. Like this now is going to infinity. So that's why it's indeterminate. All of them are going to behave that way, that there is, because of the manipulation, it might first look like, oh, maybe I think I know what that is, but that's why thinking of it in different ways can give different results. So these are all indeterminate. Do something else before you think you know what that answer is. So let's look at an example here. Maybe just of L'Hopital's rule again. So if I want to find this limit, substitute in 0. 1 minus 1, 0 over 0, indeterminate. We should be able to come up with a solution. You can pause it, try to come up with an answer. And then here's the solution for it. Taking the derivative and substituting. Now, sometimes as you're thinking about L'Hopital's rule, like and you're looking at it, let's say that this is the original problem here. If I substitute in 0, this looks like actually an infinity minus infinity example. And so I can't do L'Hopital's rule. So in some of these problems, what you'll need to do is to try to rewrite it. So in this one, we're going to combine these together to try to come up with a different fraction to then apply L'Hopital's rule for. Now I'll say this, that you can actually apply L'Hopital's rule twice or 3 times or 4 times or 100 times if you needed to, as long as the conditions are still satisfied, meaning as long as you substitute and you still get 0, 0, infinity over infinity, you can do L'Hopital's rule. And finally, the last example to look at is maybe this one. Trying to find the derivative, the limit of a function like this. Now, in terms of L'Hopital's rule, like it doesn't apply, this is not 0 or 0. In fact, as you look at this one is actually 1 to the infinity, okay? 1 to the infinity should be the indeterminate form you're kind of thinking there. So again, is it 1? Well, this one actually isn't, which is then going to maybe cause a little bit of struggle for you, thinking about, well, 1 times 1, 1. But that's not really what we're saying, because infinity is not a number, so we shouldn't really treat it that way. So in this problem, though, here's going to be the suggestion that we're always going to be stuck if we're going to keep this exponential kind of form to it. Now this isn't really an exponential because this is also a variable. So what I want to do is maybe just say like y equals e to the x over 3 plus x to the 3 over x. So with that, we're going to take maybe the log of both sides. I'd probably prefer the natural log because we have properties that are going to now let us move this down. And so at that moment, notice then we'd have like the natural log of y is the natural log of this, et cetera. Maybe write it this way. And if I'm interested in the limit now as x is approaching 0, we can see that L'Hopital's rule actually does apply here. So we can take the derivative, do all of that work. You're going to finish with something, and I'll let you try it, like the natural log of y. You should get a number over here when you're thinking of the limit of that whole thing. You're going to end up calling that 4. And in general, that's not going to be the answer that you want, right? Because we're supposed to be finding the limit as x approaches 0 of what I called y, which means I have really a representation of the natural log of y. And so knowing that this is base e, my final answer here is going to be e to the 4th as that answer. So that's a little bit here about 9.2, L'Hopital's rule. I hope that was helpful.